So let's talk about the entire chapter. We're talking about sound and hearing. Okay, first off, sound waves are longitudinal waves. They're pressure waves, air molecules bouncing back and forth in the air. Areas of high pressure correspond with our peaks if we think of a sinusoidal wave, and areas of low pressure correspond to our troughs. So like here, air molecules bouncing back and forth. Here's a crest, here's a trough. And these are pressure waves. Okay, now we've got all the stuff from Physics 1 that you did in your material science chapter about bulk modulus and Young's modulus and all that. We're not going to do anything with that in this class, but it is here. If you're curious what that pressure wave will look like, it will depend on the bulk modulus of your medium. And again, you can go back to your Physics 1 textbook if you want to read more about bulk modulus. We're not going to do anything with it here. So in a fluid, we depend on the bulk modulus, and a solid, it depends on Young's modulus and so forth. Again, this is all stuff you barely covered in Physics 1, so I don't want to spend a lot of time on it here in 2. Okay, so that was the speed of sound in a particular medium. Here are some speeds of sound in meters per second. We're going to do a lot of stuff with sound in air in this class. So every time they'll always tell us what speed of sound in air they would like us to use, because that depends on our elevation and the temperature. But a good rough kind of guide for its speed of sound in air is about 340 meters per second. And that varies, again, depending on temperature and height.
Do we need to know any of these by heart?
No, not at all. Because every problem might use a slightly different value there. You'll do some that are 344, some that are 340.
Okay.
Okay, now this slide is misleading. This is literally the formula for intensity based on the density and the speed, or based on the bulk modulus, so forth. We're not going to use any of these formulas. This is the formula we're going to use for intensity, and you will have homework problems that depend on this. The general formula for intensity is the power at the source divided by the surface area of a sphere some distance from that source. So I have some sound wave here. That sound will travel out in an expanding sphere. If I'm out at some radius r, then the intensity that I hear out here, here's me, the listener, that distance r away, is the power divided by 4 pi r squared. Now, the kinds of question we're going to ask are, what happens if you go maybe, let's make up an example, twice as far out? How does that affect the intensity? So we're not actually going to calculate a new intensity. We want that in terms of, say, some initial intensity. Is it going to be twice as intense, half as intense, 1/4 the intense, and so forth? And like we could quickly answer that. If I double R, because we have this square here, I will get a 4 in the bottom. So out here, if we call this I naught at that spot, then over here would be 1/4 as intense at double the distance. Those are the kinds of questions we'll be answering. And notice that has nothing to do with calculating the actual value. We don't need the velocity. We don't need the bulk modulus. None of that.
Is that the inverse square law?
Yeah.
Okay.
That's one example of the inverse square law. And it's literally for the same reason. That's why the electric field drops off like 1 over r squared too. That's why gravity drops off like 1 over r squared. A lot of things in nature drop off like 1 over r squared, and it's literally the same idea. They're expanding or they're moving out in an expanding sphere. And so the level you feel out here is 1 over the surface area of that sphere. Okay, now the way we usually measure sound is in the decibel scale. Decibel scale is a logarithmic scale. These intensities are quite large. So we measure sound using a decibel scale. Now this is going to confuse you. You have to be careful and read questions carefully. Notice, see the word intensity right there? And the word intensity there. You're going to get these two concepts confused in questions. So anytime I write a question, I'm always specific. I tell you whether or not I want decibels. Wave intensity is what we call I. That's the absolute scale. That's energy per unit area. Sound intensity level is how loud it seems in our ears. And that's a decibel scale. And that's measured in these things called decibels, which are 1/10 of a bell. A bell is really big, so we measure it in decibels. Okay, so let me write down this formula. In a 3 decibel sound plus a 5 decibel sound is not an 8 decibel sound. This is a logarithmic scale. It is not additive. We're on a logarithmic scale. In fact, this is what you want to memorize. An increase of 10 decibels is 10 times louder. Every time you go up by 10 decibels, it's 10 times louder. It's 10 times as intense because we're in a log base 10 system. So 20 decibels is 10 times louder than 10 decibels. Let's say a concert might be 110 decibels. That's very loud. A jet engine might be 120 decibels. So at first you think, oh, the jet's just a little bit louder than the concert. No, it's 10 times louder than the concert because I've gone up by 10. Every increase of 10 is 10 times louder. So if I have one, say, guitar amp, 1 amp, and say I have it turned up to, 50 decibels, then 2 amps is not 100 decibels. It would take 10 amps to get up to 60 decibels. It's not additive. Decibels are not a linear scale. They're a logarithmic scale. And one of the videos you'll be watching is about having, I think it's a 7 trombone, I think is the one I do. It's not 7 times louder. Okay, here's a scale of decibels for reference, just so you can kind of get an idea of how loud things are. So everything we measure in the decibel scale is in relation to this I naught, which has an intensity of 10 to the negative 12th watts per square meter. That is about the threshold of human hearing. That's like the lowest level of intensity that we can even hear. So we do everything in relationship to that. So here are the actual intensities. Here are our decibel levels. And again, I was just making up numbers on that last example. A jet is even much louder than I thought it was. This is 20 decibels louder. I said 120, it's actually 140. That means it's 1,000 times louder than what I wrote down. Okay, we're not really going to do much with standing waves or with pipe organs and harmonics and whatnot. There's a lot of really cool stuff we could do there if we were doing harmonic analysis, but it's really outside the scope of this class. So I don't really go into this at all. If you become a music major, this is kind of some interesting stuff, but I'm not going to quiz you on any of this stuff here. Resonance is cool though. I'm not going to ask you any questions about it, but it is pretty cool that if you have some kind of closed system and you pump in standing waves, waves that fit into it perfectly, then those waves will resonate. They'll cause the object to vibrate. And if you put enough energy in, you can actually cause the object to explode. And one of the videos I have for you here, this is a guy from my hometown, Jamie Vandera. He is the first person ever to use his unaided voice, no amplifier, to break a glass using resonance. And he did it on Mythbusters. He does it all the time now. He got a piece of glass stuck in his throat once because the glass exploded and went backwards into his mouth, and he had to have it surgically removed. This is not the best video. There are probably better videos of him doing this out there. This is the one I've posted. So you should watch that. It's kind of cool. Here's some other videos, by the way. These here, I think you should watch. They're very good videos. If we were face to face, we would have like movie time and we would watch these together. This is interesting. We're going to talk in a minute about breaking the sound barrier. So you guys know what happens when you break the sound barrier. You get a sonic boom, right? These are really good videos about why that happens. Well, what would happen if you would break the light barrier? Would you get a light boom like a sonic boom? And you're saying, but you can't break the light barrier. You can't go faster than the speed of light. Of course you can. You can't go faster than light in a vacuum, but in a material, light moves much slower. Through water, light doesn't move as fast as it does in a vacuum. So in water, it's possible to have particles go faster than the light goes in that particle. And what happens is you get a luminal or photonic boom. It's called Cherenkov radiation. It's pretty cool. And it literally is the luminal or light equivalent of breaking the sound barrier. So watch this. It's kind of cool.